Hey guys, Mr. Weir here. This next video you are about to see is going to be all about cooking the perfect egg. The important chemistry concepts you're going to learn about in this video are going to be temperature, states of matter, that's solid, liquid, and gases. And then the other important thing you need to remember is temperature and heat, and how temperature and heat are actually not how hot or cold something is, but rather the average kinetic energy of molecules in a system. Enjoy, but before you do this, please make sure you pause your video and have your Google Doc egg transcription notes out, ready to go. Thanks.
So probably the most important innovation in cooking in the last 200 years is low temperature cooking. You can buy what's called an immersion circulator, a unit like this, that can keep water extremely accurately heated. So this does within 1/10 of a degree or so Celsius, keeping a very accurate water temperature. A very good demonstration of that is eggs, because eggs almost can act like a thermometer, and in a very small window of temperatures between 57 Celsius and 7 degrees Celsius, that 13-degree window is almost all of egg cookery is encompassed in those 13 degrees. So at 57 degrees Celsius, in an egg, it's completely raw. However, if you cook an egg at 57 Celsius for enough time, I usually cook it for an hour, it's completely pasteurized, meaning you've killed any salmonella in it. And at 60, it's just barely set. You can see and remember, the white is made up of more than one kind of protein. So what we're doing is we're setting some of the proteins, but not others. And it's 2 degrees higher than 60. We hit the first real egg that we use in restaurants all the time, the 62-degree egg. This is the perfect egg for Eggs Benedict. Now look at that. Only 2 degrees difference. Look, the color is changed on the white. It's a lot, it holds up, but it's still got kind of a custardy, delicious, soft white, right? But notice here that egg white, there's 2 different kinds of egg white. There's thick and thin. And the thin, right, sets in a different layer from the thick and almost acts as a release agent. And when you cut it, the yolk is still runny like this. This is perfect for toast. Only 1 degree higher than 62 is one of the eggs that I think is most interesting. 63 Celsius is what I like to call in-betweener eggs. So you can see here is a yolk that is not yet set and is somewhat liquid and will eventually run out. All right, so 1 degree higher than 63, we have 64. 64 is actually a fully set egg yolk, but it's still extremely soft and custardy. So if I go 1 degree higher to 65, you start getting into what I call the Play-Doh egg yolk. At 66 degrees, it's kind of not Play-Doh anymore. It's more like marzipan. It comes up nicely, but it's still extremely moldable and creamy. 1 degree higher than that, 67, and you start to lose that effect. So if you look at a 67-degree egg, begin to squeeze it, you can see that it shatters here, it pops. Instead of, it's beginning to lose its creaminess, and it's starting to take on the kind of crystalline nature of the inside of a cooked egg yolk. 3 degrees higher than that, at 70, it's like a hard-boiled egg. One of the interesting things is that a 70-degree egg, if you only cook it for an hour or so, doesn't have any sulfurous aroma at all. It's completely fresh. There's no greening of it, right? So it's a very bright, beautiful-looking egg yolk. And when you break into it, you'll see that it is got the cooked granular structure now of a standard kind of hard-cooked egg. As you can see, from raw but pasteurized all the way up to hard-cooked egg yolk is a mere 13 degrees, just to kind of demonstrate the importance of temperature control.
Eggs. That was an enormously exciting video about eggs. If I could have you guys raise your hands right now and tell me who likes making eggs, I would, but we're not in class, so I won't. Now, there were 3 things in this video that I really wanted to review. The first of which is temperature and heat. The second of which is states of matter, and that's your solid, liquid, and gas. And the third thing I wanted to review is going to be chemical versus physical changes. So let's get into it. If you guys remember, temperature and heat are not how hot something is, but rather temperature and heat are really the average kinetic energy of molecules within something. So let's take a deeper look into that. Here we have 2 pots of boiling water. Pot 1 is, of course, under some fire, and it's currently at 200 degrees. Notice that its molecules are spinning fast. Over here we have pot number 2, and pot number 2 is at 100 degrees, so it is colder, and notice that its molecules are spinning a lot slower. So this is temperature and this is heat. Heat is honestly only how fast particles are moving. The last thing I wanted to talk about was chemical versus physical changes. First, let's look at physical changes. So in a physical change, the matter changes form, but not chemical identity. So physical changes really only change the shape, the size, or the state of that thing. For example, chopping wood, after you chop it, that wood is still wood, it's now just 2 pieces. Even melting ice, it's still just water, now it's just liquid water. Shredding paper, it's still paper, but now just smaller pieces of paper. Chemical changes, on the other hand, are a little bit different. Chemical changes change the thing itself, and they actually form new substances. So when you burn wood, you started with just wood, but you end up with ash, smoke, fire, charcoal, and more. When you mix vinegar and baking soda, you actually get carbon dioxide, and you can make some cool rockets out of that. We might do that later on. So chemical changes actually form new things.